Okay, so in this video I'm just basically going to show you like differential equations. Likewise, a differential equation relates a function and its derivatives. Maybe it's probably a derivative of y with respect to x, or that of x with respect to t, and stuff like that. So basically you have something like prime, y prime equals let's say x plus y, stuff like that. And this is a differential equation. So in this one we will expect that we have some function y that when you differentiate it, you get the derivative being y prime equals x plus y and stuff like that. So now we have techniques of like solving differential equations. Maybe if we have y prime equals cos x, we know that we'll assume that of y it's a function of x. You can write y prime as dy dx, and then we have cosine x, stuff like that. So the technique that you can use here is that you separate y terms and group them with dy, and separate the x terms and group them with dx. In general, we have something like this: f of y dy is equals to g at x dx. An equation is separable if you can rewrite it like this. Notice that here you can just have dy equals cosine x dx, and that's written in this form. Then our equation is separable. And then from then you can have integral dy equals integral cosine x dx. So you have stuff like this. And from then we know the integral of cosine x. So let's discuss the techniques that we are going to use for this. Now note that in this video I'm just going to basically focus on first order differential equation. So I'm just going to focus on first order differential equation. So we have like I said, separable equations, and that's the first one. Then we have separable equations there, the equations that you can rewrite in this form. And then you have also substitution technique. You have substitution technique. How does that work? Remember when you were like integrating, and then maybe you are integrating something like this: 1 over x, let's say 1 over x squared minus 2x plus 1 dx. When you are integrating something like this, notice that you will factor and have something like this: x minus 1 squared, and then you're going to substitute so you can find the integral. Then you let u equals x minus 1. You let u equals x minus 1, then express du in terms of dx. And then that's dx here. You just plug in, then you have integral of 1 over u squared du. So likewise, substitution helps us to like find it helps us simplify the process of solving differential equations. And then we also have like solving using the integration factor. So we can also find our integration factor of that, and we can also use the integration factor to find to make a non-exact equation to be exact. So, and then that's technically what we're going to be focusing on in this video. But then where do you use integration? Where are we forced to find the integration factor? How do we know if the equation is exact and stuff like that? So I'm just going to focus on that for now. So let's say maybe we have a differential equation: y prime minus x equals y. So if we have something like this, notice that this is a linear equation. The general formula for a linear equation is, if you can rewrite, since this is first order, you're probably going to have something like this: maybe f at x y prime plus g at x y plus let's say k at x. That will be equals 0. So you just have functions of x, the derivative, the y prime sign here, and then you have y, and then you have k at x. You can repeat the same process for the second order. You'll just add a term that contains f. That's just only a function of x, and you have stuff like that. Then the equation will be linear. So if we have this, notice that this equation is linear. But not only can you say that, but notice that here you can solve this one using integration factor, or what you can do is like you can solve it using substitution as well. So using the integration factor, notice that you have your differential form in the form y prime plus p of x y equals q of x. You need your equation to be rewritten in this form. Then you can use the integration factor to solve that equation. So now let's look at this equation. So that means we can rewrite this equation as y prime minus y equals x. Identify p of x. You can tell that that's going to be -1. P of x, that would be -1, and then your q at x will just be x. And then from there you can like find the integration factor mu of x. This will be e to the power of the integral of p at x, and our p at x is just -1. Then you integrate that, and then you're just going to have e to the power of minus x, and that's your integration factor. That's your mu of x. Now when you identified mu of x from there, that means that you can like rewrite y as that integration factor 1 over that integration factor multiplied by the integral of that integration factor multiplied by q of x, and q of x is just x, and then you have dx there, and you add a constant c, is the integration factor multiplied by q of x plus some constant c there, and then 1 over e to the power of minus x, that's just e to the power of x, and then the integral of this, obviously you're going to use integration by parts, and let's do by parts, and then from here you're just going to have like minus x e to the x to the minus x, and then plus okay, so it's going to be negative e to the power of minus x. Let's check derivative of this one. You have minus e to the minus x, and then you have plus x e to the power of minus x plus e to the power of minus x, and then the two will just cancel out, and then you'll be left with this one. Then you have something like this. Now notice you can distribute this inside. E to the power of x multiplied by e to the power of minus x, that will just simplify to 1. So you just have minus x by 1, and then e to the x multiplied by minus e to the power of minus x, that will simplify to minus 1, and then you're gonna have that c e to the power of x, and that will be the solution to, that will be the general solution to this differential equation. Okay, so let's look at another example though. Let's say maybe we have xy prime plus 2xy, let's say x squared, and then this will be equals to x cubed. Notice that this is not quite in standard form. What you need is you need y prime plus p of x, y equals g at x. I mean equals q at x or g at x or any function of x. So then we need the y prime. That means we have to divide everything by x squared. Then you have y prime plus 2x over x squared, that's just going to be 2 over x, then you have y, and then this will be equals to x if you divide x cubed by x squared. And then from then you need to find the integration factor here. Then nu of x is just going to be e to the power of the integral of 2 over x dx, and then this one is just going to be 2 ln x or ln x squared. E to the power ln x squared, let me just write that, you have 2 ln x. Notice that you can take the 2 back inside the ln, and then you have e to the power of ln of x squared, and we already know what happens when you compose a function into its inverse, and then that's just gonna be x squared. So that means your integration factor is x squared. So then we have y equals, the general formula is written like this, mu of x into the integral of mu of x multiplied by q of x plus some dx plus some constant c. And then from here you just have y equals 1 over x squared into the integral of x squared multiplied by q of x, and q of x in this case is just x dx plus some constant c. Then you have something like this, and you have y equals 1 over x squared into the integral of x cubed into the integral of x cubed dx plus some constant c, and then we have y equals 1 over x squared, and the integral of x cubed is just going to be x to the 4 over 4, and then you add some constant c, then you just have something like this, y equals x squared over 4 plus c over x squared, and that will be the general solution to that differential equation. But then notice that this is the general form of that. But now what happens if you contain something else? Maybe let's say maybe you have x plus 1 y prime is equals to y squared plus y. Notice that now we have a problem. We can't write this equation to give us this. We can't. Notice that if you try that, you'll have like x plus y prime minus y equals y squared, and then from here you just have y prime minus into 1 over x plus 1 y equals y squared over x plus 1. Well, let me just rewrite it as just 1 over x plus 1 multiplied by y squared. Now notice that now instead of having this, you have some function of y there. So this is known as the Bernoulli equation. In general, you have y prime minus or plus p of x y equals q of x y to the n multiplied by y to the n. So whenever you have this case like this, then substitute in y equals, substituting u equals y to the power 1 minus n. So when you have your equation written like this, then you substitute u equals y to the power of 1 minus n. Okay, so let's look at an example for that. You can try this one here and test yourself on that one. So let's say maybe you have y prime plus 1 over x, y equals 2y squared. How do we solve this differential equation here? So what you have is that you have a Bernoulli equation in standard form. Remember, you have y prime plus p of x y equals q of x y to the n. And then when you have something like this, then that means you can just make a substitution. Let u equals y to the power 1 minus n, and in your case n is just 2 in this case, so you have 1 minus 2, and that's just going to be y to the power of minus 1. If u equals y to the power of minus 1, we can then say that y will just be equals to remember, let me just show all steps because it might confuse you. Y to the power of minus 1 is the same as 1 over y. And then when we have this thing, you can rewrite y as just 1 over u. If you multiply by y and divide by u, you have, or if you just flip both sides, then remember this is u over 1. If you flip both sides, you'll have 1 over u, and if you flip this side, you'll just have y over 1, which is just y. It just depends on your understanding, on how you understand this thing. But then, in general, we have y equals 1 over u, then you just derive. So you have dy over dx. It's technically going to be, dy over dx is just going to be equals to the derivative of 1 over u is just going to be minus 1 over u squared. Then you have to show that you're deriving u with respect to x. Then you can rewrite y prime as minus 1 over u squared du dx. And then replace y in your equation by 1 over u. Let's do that. We have y prime. Y prime is the same as dy dx. You replace dy dx with minus 1 over u squared du dx, right? And then plus 1 over x. Whenever you see y, you replace it with 1 over u. And then you have an equal sign, you have 2. And then you see y squared, then you replace it with 1 over u. And then you're just going to have 1 over u all squared. Then you just have that. And then what you can do is like multiply everything by minus u squared. Multiply everything here by minus u squared. If you multiply this term by minus u squared, just cancel out, and then you have du over dx. And then if you multiply this term by minus u squared, notice that don't do this in the test, what I'm about to do. You have minus u squared here. I'm just showing you what I'm doing. You have minus u squared by this one. It just cancels out this minus u squared. Then you just have du dx. And then you have minus u squared by this one. Notice that this one will just cancel the square, and then you're just going to have minus u, right? So you have minus 1 over x by u. And then again, you have minus u squared by this one here. 1 over u all square is just the same as this. 1 square is just 1. So you have 1 square over u square, which is just 1 over u square. And then it just basically simplifies to just cancels out this u square, and then you have minus 2. Notice I said don't do this in the tomorrow. Okay. Don't do this in tomorrow's test. I'm just showing you what I'm doing here. I mean the step where I multiply everything with u squared. I'm just showing you what I'm doing here. But then then you have this in this form. Notice that now this goes back to this form, but now it's no longer y prime. It's now u prime plus p of x u equals q at x. And then notice that you can use your integration factor here. Then you can use your integration factor here, and you can solve for u. What's our integration factor? Okay, let me just write that. U mu of x equals the e to the power of the integral of minus 1 over x. Remember, your p of x is just going to be minus 1 over x. The integral of that then is just going to be minus ln x. And then you take the negative inside, then you're just going to have e to the power of ln 1 over x. And that's just going to be then you're composing a function to its inverse, then you're just going to have 1 over x. And then when you have this, then you can solve for u. U will be equals to 1 over mu of x multiplied by the integral of mu of x multiplied by q of x dx plus c. But then what's u? u equals 1 over y, u equals 1 over y, and 1 over y equals 1 over x multiplied by the integral of 1 over x by q of x, and q of x is minus 2 in this case, so you multiply that by minus 2 and then dx plus c. And then you have 1 over y equals 1 over x. Just flip that, you're just going to have x. And then this is minus 2, it's a constant. You can take it outside the integral. And then once the integral of 1 over x is just going to be ln the absolute value of x. But notice that you have minus 2 there. Then you just have ln the absolute value of x plus some constant c. And then further simplify this, then you have 1 over y equals minus 2x ln the absolute value of x plus cx. And then flip the sides, then you have y equals 1 over cx minus 2x ln the absolute value of x. And that will be your solution, your general solution to that. So notice in mind that I just showed you two techniques. I showed you using integration factor, and this one you already know, the separable equation. That's where you can do this. And what about the other technique? Where do you do substitution and stuff like that? I would like to introduce you to a homogeneous equation there. If you can rewrite dy dx, let's say we rewrite dy dx as some function of xy, f at xy. If you evaluate f at kx ky, if you evaluate f at kx ky, then you get some k to the n f at xy, then your equation is homogeneous. Then you can plug in u equals y over x. That's your substitution in this case. Let's say we have xy dy. Let's say we have xy dy equals x squared minus y squared dx. Let's say maybe you have this equation in this form. Notice that you can rewrite dy dx as just x squared minus y squared over xy. You cannot separate the variables. Notice that you can't separate the variables. But then if you try, now what if you would like to just say, what if I do this? What if I say I have dy, I divide everything by dx, then I have xy dy dx is just equals to x squared minus y squared. And then when I have that, I just divide everything by xy. Divide everything by xy, then you have dy dx. When you divide this one by xy, notice that this x will cancel the square there, and then you're just gonna have x and then over y, and then you have y squared there, and then this y will cancel the square, and then you're just gonna have minus y over x, and then you have stuff like this. And that's where you divide everything by xy, and then dy dx will just be equals, dy dx, take this term that side, and you have positive 1 over x y equals x over y, and you can rewrite y to the power minus 1. You can use the Bernoulli, this one. This is known as the Bernoulli substitution, the one that I was basically showing you here. It's a Bernoulli equation. So then you can do that. You can solve it this way. But if you can't identify that you can do it this way, if you look at it, if you plug k here, you have k squared x squared. If you plug k here, you have k squared y squared. You can factor by k squared. And notice that here you have kx, ky, and then you have the two k's multiplying each other, then you have k squared. And if you factor the k squared here and the k squared here, you can take that out and it goes back to its original function. Then that means that equation is homogeneous. And if it's homogeneous, do this. dy dx is equals to divide everything by the highest degree of x, then that's x squared, and then you have 1 minus y over x squared. Y squared over x squared, you can rewrite it as y over x all squared. And then if you divide this one by x squared, this will cancel the square, and then you have y over x. Then I said substitute this one. Let u equals y over x. If you let u equals y over x, let u equals y over x, and that's just the same as saying let y equals ux. It's just the same thing though. Then dy dx will be equals to the derivative of u with respect to x by x plus, remember it's the product rule, plus u by the derivative of x with respect to itself. That's just going to be 1. U by 1 is just u. Plug everything there. Then you have du dx x plus u equals 1 minus u. Y over x is just u. Then you have u squared and then over u. And then you have something like that. And then you have du dx x equals 1 minus u square over u minus u. But then you can rewrite this one over that, then you just have u minus u square over u. Then when you do that, then you have something like this. Now, one of the things that you need to realize here is that whenever you make a homogeneous substitution here, u equals y over x or y equals ux, in the end, your equation should be separable. If it's not, you've done something wrong. Then, since the denominators are the same here, you can just subtract the whole thing in the numerator. You have 1 minus u square minus u square, then that's just going to be 1 minus u square minus 2u square, over u. Is the equation separable? Yes. Du, you are dividing both sides by this one, then you just flip it over, then you have u over 1 minus 2u square. Then you divide by this one, you flip it over 1 over x dx. And then you realize that your equation is indeed separable, and this one is just going to give you ln the absolute value of x. What about this one? This one is just going to give you half, negative half, the ln the absolute value of 1 minus 2u squared. Don't forget your constant. Then multiply both sides by minus 2, and then you have ln 1 minus 2u squared. This is just going to give you minus 2 ln x, ln the absolute value of x, and plus some constant c. But notice that here you'll have ln the absolute value of 1 minus 2u squared equals ln, take the negative 2 inside, then you're just going to have ln of 1 over x squared plus some constant c. Then you need to get rid of the ln, then raise everything to e, and e to the power of this, that's just going to be 1 over x squared. Multiply by e to the power of this, is still going to give you some constant c. Then you just have c over x squared, and then here you're just going to have 1 minus 2u squared, but you're not done. U is y over x. And then if they want the explicit solution, you have to solve for y. Sometimes they can give you the condition so you can solve for c. But then you basically see what's happening here. So this is a homogeneous substitution. You can try that on multiple problems. I'm just showing you the key size ideas. I made my uploads very late and you're writing tomorrow, so yeah. So what else do we have? An exact equation. We also have an exact equation. So let's look into that. Let's do this. Let's have that there. Let's say you have mx dx plus ny, m at xy, nxy dy equals 0. You have your differential equation in this form. Technically, I haven't uploaded a video on partial derivatives. You're going to have to forgive me on that one. But the key size idea of a partial derivative, let me just show you an example of that. The key size idea for a partial derivative is that if you have f at xy equals something like x squared, y squared, plus 2xy, stuff like this, whenever you're taking the partial derivative, let's say the partial derivative of f with respect to y, when you're taking a partial derivative with respect to y, treat x as a constant. You treat x as a constant, and then you derive. We know how to derive. Let me just show you an example here. You treat x as a constant, so you derive y. The derivative of y squared, that will be 2y. So you have 2x squared y plus 2x. The derivative of y is 1, so you just have 1 by 2x. So you just get 2x. So that's the partial derivative of f with respect to y. To check if you understand, you can try to find the partial derivative of f with respect to x and check if you get it. Just pause the video and try to get the partial derivative of this one. Then it will just be 2xy squared plus 2y. That will be that. So this is a key size idea. With this one, y is a constant. So you just do that, and then that's all about partial derivatives. Okay, so I don't technically need to upload a video on partial derivatives. It's just that. Then you have something like this. Then if you take the partial derivative of m with respect to y, and you find that that partial derivative is equal to the partial derivative of n with respect to x, then your equation is exact. You can say, therefore, there exists a function f of x. There exists a function f at xy such that such that the partial of f with respect to x gives you m of xy. This one, it gives you m of xy. And the partial derivative of f with respect to y, then that gives you this function n here. And therefore, what you technically do is that you'll find f of x, y. It depends on which functions you want to use. Option 1, what you can do is like from here, work on an equation that's easier to integrate. If this equation is easier to integrate, then you'll have f of x, y equals the integral of m with respect to x, and your constant in that case is just going to be g of y. Then you add g of y, so that will be that integral, and you just add g of y, and then from then you take the derivative of that one, and then you take the derivative of this one with respect to y, and then you'll find g prime of x from there. G prime of y, I mean. Okay, so I think like if option 2, it's easier to like integrate this one with respect to y, then you'll have f of xy equals the integral of n with respect to y, and your constant is just gonna be g of x or h of x. It can be anything though, a function of x. So let's work on an example here. Let's say we have 2x minus y dx is equals to x plus y squared dy. In standard form, you need something like this, so please try to have that. So then you just have 2x minus y dx minus x plus y squared dy. This will be equals to 0. For simplicity reasons, I just suggest you do this. Notice that from the formula you have a positive. Try to keep the positive outside. So just dx, try to keep the positive outside, then just distribute the negative inside. Then plus into minus x minus y squared dy equals 0. And then from then, you find my. You derive the dx term here with respect to y. You take the partial derivative of that. You take the partial of this one with respect to y, and notice that you're just going to have minus 1. Right? And then you take the partial of this one with respect to x, and notice that y it's a constant, then you just take the derivative of minus x, and you just have minus 1. Therefore, we realize that my is the same as just nx. What does this mean? This means that the equation is exact. So we can say, therefore, there exists a function f at xy such that the partial of f with respect to x will just technically give us m, and m is this function here. You use the simplified equation, right? So m is this one. Then you have 2x minus y, and the partial of f with respect to y, then that's just going to give you minus x minus y squared. Now, which equation is easier to integrate? Both of them are equally the same to integrate. So I'm just going to take the one with x. Therefore, you have f at xy. I'm taking this one with respect to x. Then you integrate this one with respect to x. The integral of 2x with respect to x is x squared. The integral of minus y with respect to x is just going to be minus xy. Then you add your constant c. Since this is a function of x, your constant will be some function of y. Or you can write f of, g at y is fine. And then you derive this equation with respect to x. Then the partial derivative of f with respect to x is equals to, with respect to y, obviously, because the one with respect to x is just going to go back here. Then you take it with respect to y. And then this term is a constant. And then here you're just going to have minus x. The derivative of g of y is just going to be g prime at y. But what's the partial of f with respect to y is this one. So you have minus x minus y squared equals minus x plus g prime of y. And then notice that the negative x and negative x will cancel. Then you have g prime at y equals minus y squared. What's the integral? That will give you g of y. G of y equals minus y cubed over 3. That's the integral of minus y squared, minus y cubed over 3. Then your function is just this one, your solution is just this one, and then you plug in g at x, which is just minus y cubed over 3. So your solution will just be x squared minus xy plus g of y, which is just minus y cubed over 3 equals some constant c. It can be any constant. But in generally, they technically mean that it's a function of two variables at a certain point. Then yeah, then it's technically that. So that's exact equations. You can try more problems using this technique, because the video is already long and then we haven't basically covered